And we're live. Hello, hello, hello. Okay, I'll probably wait for another couple minutes. You know what? Let's just start, because I'm going to be talking for a bit. Okay, so today, we'll be doing both the AMC 12A and B. Well, I won't be doing both of them. I won't be like going over the problems or anything. Uh, I'll just be like talking about them, giving each of the here, I have the problems pulled up here. And I might go over some of the more interesting problems, but I'll just look at each problem, say, is this problem good or bad? And you might be wondering, well, what defines a good or bad problem? Okay, so a good problem is, in my opinion, so what should go on a math competition like the AMC? I think the easier problems, like problems 1 through 10, right? They should be approachable. So what that means is, okay, let me see. Yep. Hello, hello, hello. I dropped my pen. It's all right. Okay, so problems 1 through 10 should be approachable. So some new guy, he's interested in math. He's just gotten into well, I suppose the AMC 10A or B would be better for this. But let's say some guy just got out of middle school. He's in ninth grade and he likes math and he wants to try out a math competition. He should be able to look at problems 1 through 10 and not see the word orthocenter or something like that. He should be able to understand everything that's going on. He might not necessarily be able to do everything that's in 1 through 10, but it should be challenging but approachable for new students. What it should also do is hold on. I hope I spelled that right. It should separate people who are experienced with math competitions from people that are not experienced with math competitions. So for example, a really tedious problem would not be good. For example, let's say, I don't know, calculate a problem like, say, if I calculate the first 10 terms, the sum of the first 10 terms of the Fibonacci sequence. That would not be, wait, hold on. Is there a quick way to do that? Is there? I don't know if there's a quick way to do that. Assume there's not a quick way to do that, and the fastest way to do that is to just add up the 10 terms. Write them out, 1, 1, 2, 3, 5, 8, and so on. Okay, maybe 10 isn't enough. Maybe let's say first 20 terms of the Fibonacci sequence, and you have to sum all of them up. That would be a bad problem. Assuming there isn't an easy way to do it. I just came up with that. I don't really know. But yeah, I need an example. So that would be a bad problem because someone with no math experience would take pretty much the same amount of time to do that as someone with like a decent amount of uh, math experience. Because remember, this is a competition. You want to separate people who are experienced with math and from people who are not. So yeah, that would not be a good problem. That's what I mean by separate. You know what? Probably skilled would be a better term for this. And I honestly think that when you're dealing with easy problems like 1 through 10, there aren't that many opportunities for really clever problems. So a lot of people want every problem on the AMC to be really clever and to give you some new insight. I don't think that's possible. I don't think there are enough clever insights. And, well, I mean, there probably are. But I don't think MAA has the organization that runs the AMC has the capability of coming up with that many with that many clever problems. And yeah, if there were that many clever problems, probably most of them would be too difficult to fit in 1 through 10. So, those are my two criteria for the easy problems. And then for the rest of the problems, like 11 through 25, they should be the clever ones. These should be the problems that, if you're done with the competition and you didn't do them, you should still want to do them. You shouldn't walk out of the competition room and think, "Oh, I'm done with the competition." You should still be like working on the problems. They should be appealing enough and interesting enough that you are still working on them. And they of course also need to be skilled. And I think at this point, 11 to 25, you can use more complex terms that nor that they don't teach in school. They don't teach in middle school or high school. And that yeah, that would be fine. Okay, let's just get into it. This is all right. I have the problems here. So, yeah, I have every problem from the A and B, and I'm going to talk about every single one of them. All right. Problem 1. Um, I don't know why exactly it says due north and due east. What this problem is, basically, Andy leaves some point traveling at 8 miles per hour starting at 1:30, and then Betsy leaves at the same point, and then Betsy is traveling at 12 miles per hour starting at 2:30. And it's asking, when will they be exactly the same distance from the starting point? I don't know why it says due north and due east. I think because I want the problems to be skilled, a better way to phrase this would just to say, oh, they go in the same direction, right? So Andy and Betsy just go in the same direction. Of course, Betsy is moving faster, so she will eventually catch up. And just to ask, at what time will they be at the same spot? That way the question would be faster. Like you could read it quickly, and there would be more of a time gap between an experienced person and someone who's not experienced. So like, yeah, that way, because the due north and due east, it doesn't really do anything. All it is fluff. Problem 2, okay, it's all right. Problem 3 is absolute dog shit. What the hell is this? Why is that problem 3? It's just a bunch of algebra. I don't think there's a better solution. You just plug in a bunch of numbers and you make a variable for the way I did this is you put a variable for the number of students and the number of teachers will be 15 minus x since they add up to 15 and you do a whole bunch of algebra. It takes pretty much the same amount of time for an experienced person and a not experienced person. No cleverness is involved in this question. The only thing that separates people is how fast they can do algebra. So yeah, that's a horrible question. Question 4 though. Question 4 is pretty good. I like this one. It's a logic one. I've never seen something like this. Well, I've seen like somewhat similar problems, but nothing too similar to this on math competitions. And see, that's a good problem. You know what? Let's work through this. Agnes writes the following 4 statements on a blank piece of paper, and it gives you these 4 statements, which are just basically they describe the statements themselves and how, like if they're true or not, how many of them are true, and it's just asking how many of these are false. I guess think about that for a little while. How many questions are there? Usually 25, yes. Okay, the latex isn't really working. His age must be. Ooh. Oh, you can do this like, oh. Well, I mean, I didn't think of that. Huh, okay. I guess that is clever, but the thing is, you're not gonna expect that on problem 3, I guess. Whatever, I still don't really like it. Even if there is a clever solution, I don't think it's that much more clever. Face, yes, hello. Reminds me of some of the true or false tests in sideways arithmetic from ways. I don't know what that is. Okay. Oh yeah. Oh yeah, there was a square meme problem. I'll get into that later. Oh crap, wait. I just realized when I alt tab you can't see the problem. That's a bit stupid of me. Okay, I'll just keep it here. Okay. Let me pull up chat on my phone. Can I not watch live streams on my phone? What's going on? Okay, wait. Give me some time to figure this out. Uh, I don't know how to pull up the live stream chat. I go in the YouTube app and it doesn't let me watch for some reason. Can I not watch my own live stream? Oh, I think that's why. Okay, well that's annoying. I can't really look at chat now. Um, it's alright. Alright, we'll just do this problem, since it is a nice little problem. Okay. Oh, I forgot how to do this. Whatever. Okay, so at least one of these statements is true. At least two of these statements is true. At least two of these statements are false, and at least one of these statements is false. Okay, so right away, we can draw a line down the middle. Let's see. If this statement, okay, I guess we just start from, I think what we do is we start from 0, see how many are false. Like, for example, A would mean all of these are true, and we'll see what if we get a contradiction, and that'll like lead us to a further answer. Well, let's just do it. Okay, let's assume that all of these are true. So what would happen? This one is good, this one is good, but these two are not. And you'll notice that if one of these, hold on. So not all of these can be true. Let's see. What else? If three of these are true, this one is true, this one is true, and this one is true, this one is not. Okay, yeah, I think you just test around. Wait, why did I think this was a good problem? Because I remember walking out of the test, and I thought, oh, that's a pretty clever problem. I think I just thought it was clever, because I didn't see it before. But maybe this isn't that good of a problem. Okay, I take back what I said. Well, at least good job to MAA for coming up with something that doesn't look like every other problem they've ever made. Alright, so first four problems. Pretty bad, honestly. MAA has hundreds, or I don't know, hundreds, thousands maybe, of problems submitted to them every year, I think, and and their problem committee works on the problems and chooses problems that they think are good. And I think they can come up with something better than this. 4 was the only original problem I saw on here. These are just sort of copy-paste. 1 and 2 are copy-paste, 3 is copy-paste, 3 is in the wrong spot. 3 should be more like 12. It's a horrible problem anyway. I would just take it off the test. So let's move on to problems 5 and 6. 5 is a good problem. 5 is a good problem. The main reason is it's skill. And the time taken by an experienced person would be a lot quicker than the time taken by someone who's not. Okay. Oh, one more thing. The answer choices that I wanted to talk about. I want to talk about the answer choices. You'll notice that for some questions, let me find one. Yeah, for some questions, they won't ask like what is K, what is A, or what is B. They'll do this weird amalgamation thing where you need all three numbers to determine which one is which, and it makes it very hard to guess. This, they do very well. Because, look at this. If you have K, A, and B, right, you can get the answer really easily. If you don't have a single, like, the question obviously is asking you to find all three of these. If you don't have a single one of them, guessing becomes almost impossible. Look how close these are to each other. You're not going to be able to guess. And another thing that I think is really good is that if one of them is off, for example, I don't know what K and A and B are, but let's say K is 19, A is 2, and B is 3, right? The answer would then be 24. But let's say you like, miscalculate B and you get 30. You immediately know that you did something wrong, okay? And that's really important because I really hate it, and I think everyone else does too. When you do a problem, you know how to do it, but you make a calculation mistake and you get the answer wrong. This system kind of prevents that, and I think that's amazing. Okay, back to our original problem. So yeah, this is a pretty nice problem because let's just say this. Look how fast you can do this, okay? Look at this red area. Notice that if you take this red area and shrink it down, you get the white area. Uh, here. How can I do this? Can I do this? Oh, okay. We'll leave it like that. if you take this black area, right, and you you can see. Oh no, that doesn't work, does it? Okay, the point is, if you shrink the black area down, you can see it kind of fits into the white area, which means black area plus like some ratio times the black area, which I guess we'll call R, equals the side length equals the area of the square. And this is both a clever problem and it gives a lot of separation. Like well, there are other ways to do this. And you don't even someone really clever or someone really experienced probably wouldn't could do this in their head pretty easily. S- they could probably do this really quick within like 20 to 30 seconds and be done with the problem. But someone who isn't very experienced could look at this problem. It's pretty approachable. It's just a diagram and some words. There's not really anything not understandable here. And so it's an approachable problem, but it's still clever enough that they could think about this problem and they could be amazed. Oh wow, that's a clever way to do it. Something like that at the end. By the way, I will not be streaming like very much, honestly. I will probably just stream when I have something that I don't want on the main channel, if you know what I mean. Because streams don't really get that many views. Streams mainly go out to people who have already watched a lot of my videos. So, yeah, that's what I want these streams to be. I don't want them to be. I don't want to stream often. I'm still going to be mainly making videos, and I might make another one today. I don't really know. Given how bad my upload schedule has been recently, probably not. But I will try to get another video out today. Okay, problem 6. I forgot what this problem was. Pretty forgettable problem. Yeah, it's not very original. Let's just skip past that. It's a meh problem. Problem 7 is a really weird problem. I will give MAA points for being creative here, because I've never seen a problem like this before. But do I like it? Not really. Oh, well, you know what? I'll give every problem a rating from now on. I give this 6 out of 10. Problem 8. I don't really like problem 8. I think it's kind of misplaced. This should be more like problem 15, if you ask me. Um, should I go into how to do each of the problems? The main idea with this one, A, B, C, B, C, D, E. A, B, C, D, E. And, okay. And the main idea of this problem is to use the angle properties of a circle. They're inscribed angle theorem. I think it's something like that called. So for example, this is 30 degrees, so you know that this arc is 60 degrees, which is double 30. This is also 60 degrees, I believe. Did I don't think I messed anything up. BEC CED, yeah. And then you can use that to solve the question. And I think on the competition I used law of cosines. There's probably a better way to do it. I didn't really care because at this point it was pretty late in the competition. Oh yeah, I do my problems backward. So because I get bored of the starting questions and I just go straight to problem like 20 or so and I just start from there because those problems are pretty interesting compared to these ones at least. So at this point I was pretty tired and I just kind of just did calculation on everything instead of trying to look for a clever solution. Maybe that's why I don't like the beginning problems. Maybe I'm a little biased there. Okay, problem 9, complex numbers. Um, yeah, not a bad problem, not a really clever one either. So I'll give this, okay, wait, I forgot to give problem 8 a rating. I'll give this a 4 out of 10, and I'll give this a 5 out of 10. Not being very nice right now, but I promise there will be better problems later. Oh yeah, this is the square meme. There has been a meme going around that this diagram right here is a square. Why? Because this is a right angle, this is a right angle, this is a right angle, this is a right angle. Also, so you have four right angles, right? And you also have this length right here is equal to this length, is equal to this length, is equal to this length. So it's a square. Yeah. It's just a little math joke that's been going around. And I guess MAA is I don't know what MAA is doing, honestly. I don't know what goes through MAA's heads. Yeah, they just made this problem up. I think it's a pretty good problem, honestly, because it's a geometry problem. I like geometry problems, and you have to do some cleverness with similarity and ratios to get the answer. Should I be going over these problems? Do you want me to go over these? Because it would take too long. I kind of just want to, yeah, I kind of just want to go over them and give them a rating, each of them. Non-Euclidean square. Okay. Behold the square. Yeah. Um, I don't think I will do each of the problems. I might do some of the more clever ones. Like, there's one question later on that I think is really nice. But, I'll give this a 8 out of 10. Pretty good problem. Oh, look at that. They define what orthocenter means. Good job. And it asks you to find the orthocenter of a random triangle. Oh, wait. So, this is a pretty cool fact, okay? It has to do with complex numbers though, which is really weird. You would probably do some algebra, I mean, do some a bunch of calculations to find the orthocenter. I don't think there's any better way to find the orthocenter, just because the triangle looks like this. This is parallel to the x-axis. It's horizontal, basically. So the altitude from this point going down is vertical, which makes the calculations a little simpler, and you can just use point slope formula, find the midpoint, find the formula of blah 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 of this perpendicular line, using the fact that a perpendicular line slope is -1 over m of the whatever this slope is. Yeah. And then, well, honestly, I don't really like it that much. 6 out of 10. But anyway, there's this pretty cool property of complex numbers. If you have three complex numbers on the unit circle, right? Let's call them A, no, let's Z1, Z2, Z3, okay? Their orthocenter, the orthocenter of this triangle right here, oh crap, is actually Z1 plus Z2 plus Z3. You can literally add up the three coordinates and it will give you the orthocenter. And the reason for that is kind of complicated. It's because this is the circumcenter and the centroid of these three, or the center of mass of these three complex numbers would be the sum of them over 3, kind of like the mean of them, if you want to think about it like that. And there's this thing called the Euler line, where if you have a triangle, a bunch of the centers of the triangles actually land on a line. So, for example, the centroid is here, the circumcenter, which is if you take the circle, take the circumscribing circle of the entire triangle, the center of that circle is the circumcenter. And the orthocenter, which they give you the definition, you just take the altitudes. Okay, wow, holy crap, I drew this terribly. But yeah, the centers should all lie on a line. I guess the orthocenter is over there. Okay, yeah. They all lie on a line, and they lie on the line using the ratio, like it's 1 to 2 or something like that. I kind of forgot. But anyway, yeah, that's how you get this thing. You can just add up all the complex numbers. So I think that's pretty cool. That's how I did this problem, in fact, which is not normal. Okay. Um, okay. Next problem. Did I give that a rating? 6 out of 10. Yes, I did. This problem is just hilarious. Take away this for a moment, okay? They give you the definition of harmonic mean, and it's a pretty simple definition. You basically take three numbers and plug them into a formula. That's great. And then they give you this monstrosity. Isn't that hilarious? Like, someone new going into the AMC just reads this. Okay. Oh, I learned what a harmonic mean is today. Isn't that just great? And then they just see this crap. And it says, oh, all the real roots of the 4050th degree polynomial. They've probably never seen a polynomial above degree 3, okay? MA needs to chill. But, oh, this is quite a satisfying problem. It uses Vietta's theorem, or Vietta's formulas. And everything just kind of cancels out. And it's a very satisfying problem to do and to answer. So I forgot what the answer was, but I give this an 8 out of 10. Hmm, I don't remember this. Oh yeah, this is a two-part problem. I don't know why they decide to make it a two-part problem. They don't give you n. They could just say n is like, I think 1, 2, 3, 4, 6, 7, 8, 9. Yeah, n is 11, okay? They could just tell you that n is 11. I don't know why MAA has to add a bunch of extra variables and make it weird, because now it's weird to read. Does anyone feel that way? When you read these types of questions, you just get confused a little bit. Your head just like spins around a little. You don't know what is what. You don't know what n. You're confusing n and c. C is a set, n is an integer. What is going on? And yeah, I just get confused when reading these. So I think it would be better. It'd be better. MA just said n at 11 and just got rid of two whole sentences. And that way, it might be a little easier to do. They might have to bump this problem down to like question 10 or something. But I think it would be better in that. It would be more skilled. Okay. Oh, I forgot to give this a rating. Uh, 5 out of 10. Not the best problem. Okay, I can't give this a review, okay. During the test, I completely forgot the A, B, C, uh, all that crap about cubic, no, sorry, not cubic. What was I gonna say? Conic sections. Yeah, I forgot everything about conic sections. They're like formulas, like a squared minus b squared equals c squared, or something like that. I don't know. They're different for each conic section. I forgot all of them, so I couldn't do this problem, and I just guessed this. Which, props to them, this was very misleading. So this was the correct answer. So, good on MAA for making this unguessable. I'll give this an undefined out of 10. What the hell was this? This is the weirdest. Okay, I haven't looked at this problem, but I don't think there's a very simple proof for this problem. The problem asks, uh, a set of numbers is called sum free. So like this is sum free because 1 plus 4 does not equal 6. 1 plus 1 does not equal 4. Well, there's just no sums in it. But 2, 4, 5 is not because 2 plus 2 is 4. 2, 4, 6 is also not because 2 plus 4 equals 6. So it gives you that definition. And and it asks you to pick a bunch of numbers between 1 and 20. Like maybe you pick 1, 3, 5, so on, all the odd numbers between 1 and 20. And it asks you what is the largest possible number of numbers that you could pick so that these are all sum free. Now these are all sum free because and these are all odd numbers, and an odd number plus an odd number is always an even number, so therefore this is sum free. And this also happens to be the largest possible set. There are other sets, such as 11, 12, dot dot dot, all the way to 20. That is another set. These are supposed to be wacky thingies, not parentheses. And the answer is C. But this is very hard to prove, I think. I don't know. Does anyone have a proof? I haven't looked at it. So yeah, I don't know how to prove that. And I wasted some time on the test trying to look for a proof. I assume there's probably a proof. It might be simple, but I definitely haven't found it. So I don't really know what's going on. And I just kind of like quote unquote guessed 10. I was pretty sure it was 10. I looked for a bit, couldn't find a set with 11 elements in it, and so I just picked 10. 2 out of 10. Horrible question. Horrible question. This is also a horrible question. This is Quite literally, just a bunch of calculation. Actually, no, hold on. I will change this 2 out of 10 rating if someone gives me a proof that is not 10 pages long. Problem 16, another horrible question. It's a bunch of calculation. You use, well, I don't know, okay. There's nothing clever about this problem. You just plug in formulas, and you plug in numbers, and okay, it's one of those problems that would take 2 seconds if you had a calculator, and I hate those problems because they're all fluff, you know? The only thing that makes this hard is the fact that it takes 5 minutes to do. So, 1 out of 10. If I could go lower, I would, but there are worse problems out there. Okay, yeah. So horrible 3 problems over here. Does anyone have a proof to 15? It appears not. Well, there is some stream delay, so I'll keep looking for it. Okay, this one. Uh, this one, I don't know what to say about this. You just ran, yeah, I don't know what to say about this. It's a really weird problem, that's all I'll say. And the way to do it is you randomly notice that z equals 1 is a root, or something like that. It was a pretty simple number. It was like z equals 1 or something like that. And then you could factor that out and then solve the quadratic from there. I don't know. It's just I don't know what to say about this. I'll give it also give it a 2 out of 10. No, I'll give it a 3 out of 10. I'm being too mean. So yeah, MAA, please make these better. We got 2 out of 10, 1 out of 10, and 3 out of 10 in a row, and also undefined out of 10. This might be a good problem. I wouldn't know because I don't know how to do cone exceptions. Okay, problem 18. I think this was just a counting problem. I set x is less than y is less than z, and I quite literally just counted. 1, okay, so I went 1, so wait, no, hold on. Yeah, I just listed them all out anyway and multiplied by 6 because you can kind of like order them around. For example, if x equals 1, y equals 2, and z equals 3, there are 6 different ways to order them around. 1, 3, 2, 1, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. There's 6 different ways to order them around. 3 factorial. Yeah. So, okay, question. I'll give it a 6 out of 10. This one, you use Vieta's formulas. I don't really like how it, you know what, I take that back. I like I love it when problems use Vieta's formulas. Because, okay, first of all, they're commonly used. It's it's not that hard to derive them. So if you're clever, you could like factor this out into the roots. This expression right here equals x minus a, x minus b, x minus c, and you could solve and literally just derive Vieta's formulas, and then you can manipulate your sums to get this. Pretty satisfying problem to do. I'll give it an 8 out of 10. So yeah, uh, I don't know. I think I really like Vieta's formulas because they're a mix between satisfying to do and also if you've never seen them before, which is quite rare for someone who's gotten to problem 19, you still have a chance of finding them out on your own. Hold on. Is the stream doing? Yeah, stream is doing fine. Oh wow, the lighting is really holding up. Okay, problem 20. Ooh, a bit strange. Never seen a problem like this on the AMC. I'll give it a 7 out of 10. You just split the shape up. It asks you to find the volume of this pentahedron, and it gives you a bunch of measurements. All this fluff, by the way, is just telling you exactly what it says on the diagram. Like it says, oh, this length is 7. This length is 13. Great, I can see that. I don't get why they do that. So it's always fluff. And then they could have just gave us this, gave us the asked us the volume of the pentahedron, and it would have been the same exact problem. Well, I guess it would have been a little more unclear. They should have labeled like these or something like that. But yeah, you ended up making a 3, 4, 5 triangle. It wasn't that much calculation because a lot of things canceled out. There weren't any square roots. Well, there was square roots in the intermediate step, but they immediately canceled out into a 5, 12, 13 triangle, which was kind of nice. And yeah, okay. You know what? I'll bump that up to an 8 out of 10 because I've never seen that before. And I think that's a great thing. That another problem that I've never seen before. MAA is doing something original. Let's see here. Yeah, you just simplify a bunch of stuff out, and I think there was a point where you just kind of tested stuff. Yeah, I don't like this problem too much because it is kind of tedious, but I will give it a 7 out of 10. Not bad, not bad of a problem. Three real numbers. Oh, oh. Okay, we will do both of these problems. Both of these problems are good. This one gets a 10 out of 10. This one gets a 9.5 out of 10. These are two really good problems. Well, actually, you know what? I'll bump this down to a 9 out of 10. Because it's not exactly the most original thing you've seen. Okay, so let's look at them. Why not? Three real numbers are chosen between 0 and 1. So you just randomly pick three real numbers? Well, of course. Yeah, okay, that looks a little more random. What is the probability that the greatest of these three is greater than 2 times each of the other two numbers? Like, for example, this would work because this is the greatest, and this is half of the greatest, and half of the greatest is greater than each of the other two numbers. And it asks you, what is the probability of that? The way to solve this is to add some dimensions to the problem. So instead of picking three real numbers from 0 to 1, well, you still do pick three real numbers from 0 to 1, but you do it on a cube. Or at least this is the way I did it. I think that there are other solutions. So here's 0. The x-axis goes to 1. Y-axis goes to 1. Z-axis goes to 1. So you see what we're doing here. You see what we're doing here. Let's say we can form kind of a correspondence between these two, okay? Let's say we picked like 1/4, 7/8, and 2/3, okay? What we would do here is we would pick 1/4 right here, uh 7/8 right here on the y-axis this time, not on the same axis. We've kind of split up the three numbers into three different axes. And the last one, 2/3, would be right here. And we could turn all these into a point, right? Because we've just picked 1/4 as the x-coordinate, 7/8 as the y-coordinate, and 2/3 as the z-coordinate. So this describes a point within this cube. So instead of picking three random points on here, we are picking one random point within this cube. Now, if you have seen a similar problem before, you will know how this works. You will know this little trick, okay? But there's still more to do. If you've seen this similar type of problem before, you don't immediately get the answer, okay? You have to do some manipulation. Okay, let's move this over here. Uh, okay. So I think what I did on the competition is I just set A is greater than B is greater than C. Yeah, this is just a thing to make my life easier. So I just made, oh, okay, wait. X is greater than Y is greater than C. Okay? And, and now we have two equations. X is greater than 2Y and X is greater than 2Z, right? Okay, I don't know why I added the greater than or equal to sign. It doesn't really matter. We're dealing with infinity, so the probability of x and y being equal or x and 2y being equal is 0. So it doesn't really matter. So we have these two. And what we now do is we take a two-dimensional slice of the cube. For example, we could take the xy plane here, x, y, and z, right? So we take the xy plane. We kind of take a slice this way. Okay, well, I can't really do it, but we take a slice like this. Um, yeah, you see we took a slice. Something like that. I hope you get what I mean. And now we can plot x is greater than 2y, like we normally would on a two-dimensional graph. So that would look like we would first plot x equals 2y, which would be this, with slope 1/2, right? And this part would be shaded in for x is greater than 2y. Now z doesn't matter. Okay, so let's just draw that here. It goes like this. Now z doesn't matter, right? So we can just extend this. No matter what z is, this line will still look the same. So z could be 1, okay? Line still looks like this. Still looks exactly the same. So what we get is this volume right here, taken up by this triangular prism, right triangular prism. You see this thing right here? This is one of the faces. This is the other face. We get this right triangular prism. But we also have this other relation, which we kind of just do the same thing with the x and y plane, and we get, okay, with the x and z plane, I mean, the x-z plane, we get this up to here. We get another right triangular prism. I know it's getting kind of hard to see, but what we need to do, both of these inequalities are true. Both of these inequalities are true, right? So we need to take the volume in common from both of those triangular prisms. Yeah. Okay, yeah, I said that right. So, this requires some 3D visualization, which is fine for problem 22. And you end up getting a shape like this. It is a square pyramid. Oh, I would love to have the line tool, by the way. I wish I could just press Y and draw the square pyramid like I normally would. But no, the line tool crashes Pencil 2D, so I will not be doing that. Yeah, I still haven't switched to another drawing software. A few of you said to use Krita. I tried to, but I just got lazy and I just didn't do it. Anyway, we have this, and it's pretty simple to calculate the volume, and you do some other stuff. I forgot what exactly you do, but you eventually get the answer. And it's a really clever problem. The only reason why I would give it a 9 out of 10 is because I've seen kind of similar problems before where you take this and turn it into this. I've seen that trick before. It's a pretty common trick, and it deserves to be because it's a really clever trick. So, yeah, it doesn't earn the 10 out of 10. This earns the 10 out of 10. Problem 23. I'll give you some time to think about that. And I'll try to pull up the stream on my phone so I can look at chat. Okay, but I should probably write that down. Someone comes in and and I'm just looking at my phone. Okay. So, okay, this is a class now, okay? You have until whatever 06 to like look at this problem. And I'm just going to do nothing but try to find chat live. Okay, how does this work? It doesn't even show up. Yeah, I can't look at my what the I think I have to sign out of my Google account, which is really annoying. Settings. Oh, look, it shows that I'm live. Oh, wait, what? Why can't I see it? Switch account again. Okay, I'm a standard moderator. Wait, what? I got really lucky. Okay. Alright, yeah, I can look at chat now. Perfect. I will put that there. Yeah, okay, let's go. Um, Hopefully you had some time to look at that. Yeah, this problem is really nice. So, what do you notice in common about these fair numbers? They purposely only gave you 3 examples. They didn't give you more examples because if they had given you an example like, for example, okay, I just said example like 20 times. 1, 2, 4, 8, 9, 6, 3, 6, 5, 3. You might have noticed, wait a minute. The numbers go up, and then down. And it peaks at 9. And if you test it on these numbers, these 3 numbers, you'll see that they do the same thing. So, yeah, that's pretty much a fair number. And no digit is adjacent to 2 greater digits. This pretty much translates to the number goes up and then down. Now, why is that? Okay, wait, chat is kind of distracting me. But okay, I should probably put it over here and only look at it when I want to look at it. Alright, so why is that? Well, first let's verify that this works, okay? No digit is in a sort of K, right? If a digit is adjacent to 2 greater digits, then that means the digit on the left is greater and the digit on the right is greater. So it's in a sort of value. So what this means is no digit is adjacent to 2 greater digits. There are no values in this number. The number doesn't go like that. For example, 1546 does go like that. 1, 5, 4, 6. There's a value right here. 4 is less than 5 and also 6. 3, 2, oh, wait. Why is that a what? Oh, it says it has no zeros. Okay. Yeah. And 3, 4, 3, 2, 0 are not. 3, 4, 3, 2. Okay, yeah, that's another example of the no digit is used more than once. Okay, but yeah, this just translates to there are no values. There are no values, which there are no values means it's just a mountain, which kind of makes sense. And that's also pretty clever. I've never seen that before. So that's already one part of the problem that I've never seen before. Okay, now at this point, you might think, oh, I might do casework. For example, I'll start with 9, like, when 9 is the greatest number. Because you're going to have a mountain, right? You might as well do casework on how tall the peak is. And then you can count it like that. But now you encounter your second problem. You see, if you make this connection, you don't immediately get the answer. You still have to think, which is amazing. And which is really fair for problem 23. That was a good joke, right? Okay. Anyway, uh, yeah. So at this point, I was thinking, oh, let's do casework on 9, 8, 7, and so on. For 9 numbers, you would have digits 1 through 8 that are that you could use in the fair number. So you have 8 numbers, right? You have 8 numbers. How are you going to order them? How are you going to count this? And MAA makes another, well, I guess, I don't know if MAA makes this question, but thank God they picked this question, because this question is amazing. There's another brilliant insight, okay? Look at each of these numbers, okay? Each of these numbers can either be 1, not in the number, not in the fair number. 2, on the left side of the 9. Or 3, on the right. How does that work? How does that make any sense? Let's say that I have 1, 2, 3, 4, 5, 6, 7, 8, okay? And 1 is on the left side, 2, 3, 4 are not here, 5 is on the right side, 6 is on the right side, 7 and 8 are on the left side. So we know that 1, 7, 8 are here, and 5 and 6 are here. Now, we know that it's a mountain, right? And all of the numbers are distinct. All of the numbers are different, which means we just put 1, 7, and 8 in order. 1, 7, 8. Now they're in order, right? They were already in order. And now for 5 and 6, we put them in backwards order. And now we have our fair number. and each fair number corresponds to one of these. It's another one-to-one correspondence. Another really clever trick used by this problem, which is absolutely amazing. So, okay, let's do another example. This time with 8, okay? For 8, I'll get rid of, I'll move down here. I'll zoom out a bit so you can still see the problem if you just came in. For 8, you can use 1 through 7, right? Numbers 1 through 7 are available to be used in the fair number. Let's say we pick 3 to not be in the number, 1 and 5 are on the left side, and the rest of them are on the right side. So 1 and 7 are on the left, 2, 4, 6, and 7 are on... 1 and 2 are on the left. Wait, what? 1 and 5, okay. 1 and 5 are on the left, 2, 4, 6, 7 are on the right. You order 1 and 5 in an increasing order, so your number is 1, 5, 8 so far, and you order these 4 in decreasing order, 7, 6, 4, 2. So it goes up and then down. We just made a mountain. You go 1, 5, 8, 7, 6, 4, 2. It's a mountain. So that's how we count this. Brilliant insight number 2. And now, okay, I'm only speaking for myself here. When I got to this point, right, I immediately thought, hey, let's do casework on what the top number is. The casework in itself, I think, is not that easy to spot. For maybe because maybe there's another solution that uses, like, for example, well, I don't know, that doesn't require the casework. But what you'll soon realize is that for 9, right, for 9, for 9 is 1 through 8, right? You have 3 to the power of 8 possible choices, because there are 8 numbers here, and there are 8 distinct numbers here, and each of them can be either not in the fair number, on the left side of the fair number, or on the right side of the fair number. 3 possible options and 8 things. So it's 3 times 3 times 3 times 3, 8 times. 3 to the power of 8. For 8, you can use numbers 1 through 7. It's 3 to the power of 7, so you add 3 to the power of 7. And at this point, you realize, oh, I see where this is going. And you just plug this into the geometric series formula. A 1 minus r to the power of n over 1 minus r. Or, if you don't know if you don't know this formula, or if you forgot it, don't worry. You can just do this. You can write out the expression, right? And realize, if I multiply 1 minus 3 to this, a bunch of things will, if I multiply 3 minus 1 to this, a bunch of things will cancel out. This expression times this expression is equal to 3 to the power of 9 minus 1. And now, we just divide both sides by 3 minus 1, which is 2, and we just get our answer. And, okay, yeah. So, well, let's do that right now. What's 3 to the power of 9? Minus 1 over 2. 9841. Boom, it's right there. It's right there. And everything about this question is just perfect. And look at that, it has no zeros. It has no zeros. There are no weird cases, okay? If this thing weren't here, the problem would be so different. Because 0 is a weird exception. It can't go on the left. There are just like some weird edge cases, I think. It would just make the problem a lot worse, and everything just comes together so beautifully for this question. It's unguessable. If you don't know all of this, if you didn't go through this entire solution, there's no way for you to guess it. But if you did it, it's very unlikely. If you genuinely went through all these steps and got this, and there's not very much calculation involved, so it's really hard to make a calculation mistake. And so, in other words, if you know how to do this question, you got the right answer. Everything is perfect about this question. Okay, you know what? You guys are getting tired of me talking about problem 23. But anyway, that is the best question I've seen on the AMC for years. You know what? I will talk about another problem. The last really good problem was 2022. Okay, I think it was 2022. I don't really remember. It was this. Like it gives you the numbers 121, 112, 11, 111, 2111. Yeah, if you've been on the channel for a bit, you'll remember this. I featured this in a Two Truths and a Lie video. I think it was, I forgot which one it was. It was pretty early on, like number 15 or so, something around there. But yeah, I featured this question because it was that good. It was an amazing question. It asked how many of the like listed out 10 of these numbers, right? You can see the pattern already. So it listed out 10 of these numbers. It asked how many of these are prime numbers. And the answer is none of them are because 121 equals 11 times 11. This equals 11 times 101. And here 101 times 11. If you multiply this out, you can see you get 101. This digit is blank. 101. Wait, wait. No, I did something wrong, did I? Didn't I? Yeah, yeah, wait, hold on. Anyway, you do something like that. Oh, sorry, it's 111 times 101. Yeah, yeah, yeah. You can see if you multiply 111 times 101, you get 111, and then these two are blank, and you get 111. And it beautifully comes together and becomes 11211. And you can see the pattern continues. 1111 times 11001, right? These are all composite numbers. None of them are prime. And that was the answer. I got that question wrong on the 2022 AMC. But it doesn't matter because it was it was incredibly smart. It was incredibly clever. And this question reminds me of that. Everything is just amazing. Okay, problem 24. This one is kind of easy for problem 24, I'm not going to lie. This could probably be a little earlier, probably around question like 18 or so. Um, I'll give this an 8 out of 10. Not a bad question. Actually, no, 7 out of 10. Because the question is significantly sped up by knowing what tangent of 15 degrees is, and that's not what math competitions should be about. You shouldn't have to memorize tangent of 15 degrees. Problem 25. Oh yeah, look at this. Holy crap. MAA got this question wrong. The Mathematical Association of America got the problem on their test wrong. They put the answer as 50. Okay, on the test, there were only these 5 options. The answer was F, 8. I mean, not F. They added that in. The answer was just 8. None of these answers were right. I don't know what to say. I'm just gonna give it a negative infinity out of 10. Because this happened last year too. MA has no excuse. This is America has the best math team on earth, and apparently we can't make a test without a mistake. They made a mistake last year too on the AIME, which is like a follow-up. Yeah, law of cosines. Yeah. Wait. Yeah, on this question. Yeah, there are quite a lot of ways to do this question, which is why it scored so high. But it just becomes way easier if you know tangent of 15, which I don't really like. And that's all for A. Um, A was not the worst test in the world. I think it was better than last year's. It was significantly downgraded by the fact that they got a question wrong, but I won't complain too much. Yeah, let me see what the chat. Yeah, that's what I'm talking about. They screwed up AIME 2024 problem 12. I don't know if we all get the problem correct or not. Hmm, yeah, I'm not really sure. Okay, let me see. Okay, alright. Okay, enough reading chat. Back to the stream. Okay, really nice problem. I'll give it a 9 out of 10. It's quick, simple. Yeah, it's just a great problem. Problems like these should be what makes up the first 10 because you do them really quick. It doesn't really waste your brain power. It's a pretty simple calculation. And yeah, this one. Hmm, I don't know about this one. Because remember what I said at the start of the stream about how someone who hasn't done math competitions ever before should be able to walk into the AMC and know how to do at least somewhat, like know how to do maybe like the first 4 or 5 problems. They shouldn't get screwed over completely. They should be able to do a few problems. This is not one of them. Because honestly, this problem is quite difficult for someone who has never seen a math competition before. Because think about this. They're in 10th grade. They haven't really learned that much stuff. They don't realize that they don't know what modular arithmetic is. They don't know any of that. The only chance they have of solving this problem is literally writing out a bunch of numbers, 1, 4, 9, dot, 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 and realizing that it makes a pattern. Because put yourself in the shoes of someone who has never seen math competition before. Put yourself in the shoes of someone who has just finished algebra or geometry, okay? The most advanced math they know is the inscribed angle theorem. And they probably forgot that already, okay? They're going to look at this problem. First 2025 perfect positive squares. That's pretty much impossible. Can you solve it quickly? Because no, no, no. Wait. You're asking if hold on. This problem, they're not all divisible by 11. For example, this one is not divisible by 11, and neither is the next number. Every other number is divisible by 11, I believe. So yeah, you're gonna have to be a little more clever. And other divisibility tests don't work either. For example, 3 only works every 3 numbers, and the next number is divisible by 3, and so on. Okay, back to this. So I'll give this a 4 out of 10, simply for the fact that it's unapproachable. This, it's a meh problem. It is approachable, I will give it that, but it's computation. So I'll give it a 6 out of 10. This is also, yeah, I don't like this. You know what, I'll give it a 2 out of 10. Because I don't recall ever learning what base 7 meant in school. And I live in the US, which means that a lot of other people who have like gone through the school system without any math competition training have also don't know what base 7 means. So this problem would just be completely impossible for them. And I'll make that a 1. Okay. Oh, hey, the thumbnail problem. Oh, yeah, yeah, yeah. You clicked on this. You clicked on this stream. The thumbnail says problem 5 out of 25. You know, I've seen it says problem 7 here. I took the online version. I think like most people who take the AMC take the online version, and they screw up the problems. They like mess up the order a little bit to like make cheating a little harder, right? So, and when I got to this problem, when I looked at problem number 5, all I could think of is genuinely how is this in the number 5 spot? This is the most unapproachable thing I've ever seen. How is this supposed to be doable for someone who has just learned, who has never heard of trigonometry before? Wait, honestly, wait, hold on. What is 11th grade math? 11th grade math is pre-calculus, right? Yeah, it would be pre-calculus. They've just learned what a log is. How are they supposed to do this? They don't even know what this means. They don't even know what the sigma notation means. They've never seen it. They might have seen it, but they just like dismissed it as scary math, and they just moved on with their day. Because the first time you see this is in the last unit of calculus. The first time you ever see this. I'm pretty sure. Yeah, is in the last unit of calculus. of calculus BC, not calculus AB. They have never seen this before. There's no explanation as to what the hell this thing does, which is just I don't know what to call it. This should be I'm conflicted about this problem because it's a really neat problem, okay? It's a telescoping series and once you like uh yeah, it's a telescoping problem. What that means is like you can find out another way to rewrite this, and since this is an infinite sum, you okay, I don't know how to describe a telescoping series, but everything just cancels out and it's really nice. So, I like that part of the problem. But I don't like just look at it. Just look at it. If someone yeah, if someone on the test sees this at problem 5 and I did, which means that a lot of other people also did, they'll notice that oh, the problems are getting kind of harder. They're going to quit. They're never going to do math competitions again. And MA wonders, oh, why are no one doing math competitions? Our numbers used to be so much higher. Yeah, this is why. This is probably why. You should probably, I'll give this a 5 plus or minus 3 out of 10. Because the problem part of the problem is really clever and really nice, but no, you know what? 5 plus or minus 4. But the other part of the problem is just unapproachable. So it's really nice. This is a really nice problem for someone that's experienced with math competitions. For someone who has never done math competitions before, this is hell. Okay? Yeah, that's my rating for that. And let's go back to this. What even is problem 5? Problem 5 is so goofy. So, this has one solution. It just says least possible value. Yeah, I don't know what to say about this. I guess I'll give it a no, not a 2. 2 is too low. I'll just give it a 5 out of 10. That is a weird problem. Um, this is not a bad problem, honestly. What this one does is, the key idea is that this number is divisible by 36. And I appreciate that they framed this problem as a real world scenario for because it is problem 6, so it's pretty early in the competition. So a lot of people who have never seen math competitions will go in here and they'll be like, "Oh, okay." They'll read the word problem. It's more familiar to them. But and you can see that like in the later problems, they just don't do this at all. They just yeah, there's pretty much no word problem to it. They just tell you 3 concentric circles. What is s squared? That's all they say, which I think is a really good thing. So props to MAA for that. And yeah, it's a nice divisibility problem. Nothing too creative, but again, I said this at the start of the stream. I'm not looking for creativeness in the first 10 problems. They should be approachable, and they should also set a time gap, which this problem does. So 9 out of 10. I'd be really happy if the rest of the problems 1 through 10 were like this. MA would it would be great if that could happen. There are integers a and b such that blah 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 has 4 plus root 5 at the root. What is a plus b? Oh, one more thing I want to say. It's completely unrelated to this problem, but I don't really like complex number problems. Like, look at this. This looks so forced. Do you know what I mean? It doesn't look like it should be there. If you ask me, complex numbers don't really belong in competition mathematics too much because there's not really too much elegance to them. Right now, there's not any. If you look through this competition and look, that looks pretty forced. This is like all the problems with the complex numbers. They're a lot more computation heavy. They're a lot more gimmicky. You can see over here there was another one. Where was it? Yeah, here's another one. That just feels it just feels really weird. It's like all of this could be done with like regular coordinate geometry or it could just be replaced. I don't think complex numbers should be in the AMC. even though it is AMC 12. Because a lot of people, like 11th graders, have to take AMC 12. A lot of them have never gotten to complex numbers yet, or at least they forgot them. And for good reason, because they're the most boring thing ever. But I think logarithms should stay, because logarithms you can do cool stuff like that. Logarithms have some pretty cool properties. Um, okay, I already rated that problem, I already rated that problem. This problem, oh yeah, this problem's pretty cool, I guess. You just use the fact, I think it's called the fundamental theorem of algebra or something. I don't really know the exact name, but you know that the conjugate is also a root. So 4 minus root 5 is also a root of this polynomial. You expand this, and you just find the last root, which is pretty simple. And it uses the anti-guessing. And yeah, solid problem. 8 out of 10. Nothing wrong with that. Nothing too good about that either. But it's the first 10 problems. What is the tens digit of 6 to the power of 6 to the power of 6? Again, this is not really approachable. I mean, I guess this isn't too approachable either, but you should know that if r is a root of a polynomial, then x minus r. Yeah, you learned that in x minus r is a factor of the polynomial. Yeah, you learned that in algebra 2. You use it quite frequently in algebra 2, in fact. So yeah, I'm fine with that problem. But this problem is not approachable because again, it's modular arithmetic, which is people are not familiar with that, and I don't know. What do you guys think? Complex numbers and generating functions. Okay, Okay, first of all, I've never really seen complex numbers used in generating functions at all in the math competitions, so I don't think that's a really valid argument. So, yeah, I've never really done them either, because pretty much all my experience has been with math competitions. And, like, even in proof-based competitions, I've never seen those. I've never seen that used in a single solution. Okay, yeah. Alright. Back to this problem. Yeah, not very approachable, so 4 out of 10. It's even less approachable than the other one, so I'll give it a 0 out of 10. But it is problem 9, so okay, yeah, I'm really being indecisive, but 2 out of 10. The main reason I said that about the complex numbers thing is because think about the USAMO or on the International Math Olympiad, IMO, right? When you see complex numbers being used, they're usually not being used for their elegancy. They're being used because you want to plug a bunch of numbers into geometry and hope that complex numbers spits out something useful. I s- oh, okay. Yeah. Yeah, I don't like modular arithmetic either. I don't like number theory as a whole, but I'll try not to let that bias my ratings because, yeah, I don't want to be biased. Ooh, this one uses mass points. I really like mass points. Uh, it's not approachable though, I guess. So I don't know what to rate this. But I'm sure that, yeah, everything that you can do with mass points, you can also do with similar triangle. Mass points is a method where, here, I'll just, yeah, quick lesson on math points, I guess. I think everyone in the chat probably does math competitions and knows what math points is, but I think they're pretty cool. So you have a 30, 60, 90-degree triangle, blah, 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 blah. Yeah. And you have this, and you have this, a median. Okay, and the median is just like this point to the midpoint of this length, right? All right. So what mass points is you assign a sort of mass to every point so that they cancel out. For example, let's just say the mass of this point is 3, okay? The first point you have complete freedom over. This point then would also be 3 because they balance each other out, right? Imagine this is a seesaw with this as the fulcrum, right? You need this side, these two masses need to be the same. So since we already just we know, or I guess we just randomly put that this is 3. This also has to be 3. And now the fulcrum has mass equal to the sum of these. So 6. Okay, don't ask me why yet. We're going to get there. And now we also know that this is a 30, 60, 90 degree triangle. And guess what? They also have this cool property where the ratio of their lengths is 1 to square root 3 to 2. So this is 1 to square root 3, and we're going to ignore the 2 for now, because we're going to do it on this, which is also a 30, 60, 90 degree triangle. You can find that by angle chasing, just randomly throwing angles around. And we do the same thing. This length will be, sorry, this length will be square root 3 times longer than this length. So it's 3 square root 3 times square root 3, which is 3. So the ratio of this length to this length is 3 to 1. Great diagram we drew here. But anyway, you can see that if we're still using mass points, then the mass of this point right here would be 1. Because 1 times 3 is 1 times 3. It's 3 times 1. Yeah, a little bit of physics there. That's why they call it mass points. And the fulcrum would be 4. And now, because this point has mass 4 and this point has mass 3, we know that this length to this length is 4 to 3. And we get our answer. I don't know why the hell it says x over x plus y. That's just weird. Yeah, it's 3 over 7, because 3 over 3 plus 4. 3 over 7. Let me drink some water, my throat's getting... Yeah, okay, yeah, I don't know why they said x over... Some would have been the exact same if they had asked for x plus y. Yeah, those are mass points. Anyway, oh yeah, the point I was trying to make is that anything you can do with mass points with this strategy that we just did, you can also do with similar triangles. Uh, it just takes a little bit longer. So yeah, this is kind of approachable. Even though it would take quite a bit, like quite a long time, but think about it, if you're only doing like 10 questions and you're maybe skipping a couple of them, then you have quite a long time to work on each question. You have like 10 minutes for each question, and 10 minutes is definitely enough to solve this with similar triangles. And it allows for some error as well. Maybe they try some other methods and they don't work, and they eventually settle on similar triangles. And now we're getting into the harder questions, which these questions I would be fine if they weren't approachable by someone new to math competitions. With that being said, this is still kind of approachable. It's some simple combinatorics, not too difficult, but it would be quite difficult for someone who had never studied combinatorics before. But all of the stuff in combinatorics is quite logical, and you can come up with it by yourself if you're clever enough or have had some experience with it before. And I'll give this an 8 out of 10. This one, I forgot to rate. I'll also give it an 8 out of 10. Next. Okay. Windshield wiper, it looked like this, okay? And this is 3 and this is 3.5. It gave us those measurements. This is kind of weird, because this doesn't really look like a windshield wiper. And for a while there, I thought this was like a side view. And it was a side view, and like this is the arm. This right here was the arm, and like this right here was the glass. Like the glass was over there. The windshield was over there. So I got a little thrown off by that. I think MA should be able to do something about that, make it a little more clear, but maybe I'm just stupid. But I think it's a pretty cool problem. I've never seen that before. I'll give it an 8 out of 10. 3 8 out of 10s in a row. MAA is doing good. This is how they looked at. Oh yeah, they do look like this on buses, but yeah. Oh, I guess I just haven't been on many buses. Okay. A circle has been divided into 6 sectors. I don't remember this problem. Oh yeah, it's another combinatorics problem. At this point, they don't need to be approachable. 7 out of 10. 6 out of 10. I don't really like this one for some reason. It's not very creative. Feels copy paste. Like, look how. Mm, this one is a little more. I feel like it was a little more satisfying to solve than this one. This one is kind of. Problem 14 is kind of strange. The average of the first three terms in the sequence is 2025. And then it gives us this fancy ass definition. And all it means is that the average of the first four terms is 2024. And it keeps going down. The average of the first five terms is 2023. I don't know why they had to have, like, they could have just said that. It would have been a lot easier to understand. But again, maybe. And I've been doing competition math for a while, so you'd expect me to be used to this, but I'm still not really used to this. It would be way easier if you had just copy pasted this, right? You would just taken this first fact, copy pasted it down, change the numbers to 4 and 2024, copy pasted it down one more time, change it to 5, 2023. It would be a lot easier for me to read. I don't know if anyone else feels that way. Do you guys feel that way? Does the wiki not have the images? Oh yeah, random math does have the images. I think at this point, yeah, because the test was quite literally yesterday, so I went to random math for the rest of the questions because AOPS literally did not have them. AOPS just ran out, I guess. Which understandable. We were only allowed to talk about the problems starting today. Okay, anyway, the answer was 1014. Uh, this is a creative problem, I'll just say that. I've never seen something like that before. Ooh, I like this one. This one uses similarity. You can, you see how this is sort of similar to a trapezoid in 2 dimensions? This would be the 3-dimensional analog of a trapezoid, probably. Uh, but what you can do with a trapezoid is you can extend it and make a triangle. And now you have these two triangles are similar, which is quite a powerful property that you can use. And in fact, that's how you solve this one. You extend these four down, make a sort of, hold on, let me draw this. Yeah, you make a sort of pyramid, and then you solve the question. And you use similarity to do it. Uh, for example, like this pyramid, this bottom pyramid, and this pyramid right here, and the whole pyramid, they're all similar. All three of them are similar. And you can, for example, like this small one at the bottom has a 1 by 1 square bottom. This one on the top has a 3 by 3 open square top. That means the top one is 3 times taller than the bottom one, meaning the volume is 27 times greater. And you can do the same thing for this blue one right here, I guess. It's 8 times greater than the small one. You can like do a bunch of ratios, blah blah blah. Pretty good problem. I'll give it a 9 out of 10. If you can't tell already, I like the B a lot better than the A. Hmm. Yeah, this one is some trigonometry, and it requires you to memorize a trigonometric identity. Either memorize that or memorize what sine of 22.5 degrees is. Yeah, I don't really like that. But it's not the worst problem in the world. I'll give it a 6 out of 10. I mean, it doesn't require you to. Oh, well. Yeah, it doesn't require you to memorize those things. One of those things. If you don't, you're gonna have to derive them, and half-angle identities are quite hard to derive. Or at least, people don't go walking around with that knowledge. Oh yeah, this is a horrible problem. Well, okay. I got this one wrong, so maybe I'm a little biased, but come on. If you're gonna do combinatorics, don't do it like this. This is quite literally just like well, you just do a bunch of casework and just count them all, which is not really fun at all. So, I don't really like it. I'll give it a 5 out of 10. I would give it lower, but I did give it wrong. But I did get it wrong, so I'm probably kind of biased. So I'll up it a little bit because I don't really like this problem. It's not what math competition should be. You just check a bunch of cases. Or at least that's all the solutions that I saw online, is check a bunch of cases. Aren't memorizing, because you can use angle. Oh, could you use the angle bisector theorem? Oh, you could. Yes, you could. Oh, yeah, yeah, yeah. Yeah. You know what? I'll bump this up. And I'll also go and bump the other one up. Number 24 of last test, but that one's, yeah, okay, wait. Yeah, this one, I'll give it an 8 out of 10. Because I just realized, yeah, someone in chat said, yeah, you can just use, no, get out of here. No, I'm not an adult. Yeah, I'm still in high school. This and the 10, 15 aren't memorizing because you can use angle bisector theorem. Yeah, thank you. Thank you for that. I didn't realize that. Can you derive the half-angle identities using the angle bisector theorem? Probably not, right? Okay, you know what? I'll do that later. I'll do that later. Back to the point of the stream. Ooh, this one is pretty cool. I like this. Even though it is a pretty standard Markov chain problem, uh, well, I don't really know. Maybe I just really like Markov chains, or maybe not. I don't really know, but this problem was pretty satisfying to do. So, and like it was quite a neat outcome as well. Like the numbers weren't really big. It was a pretty satisfying answer. I'll just say 8 out of 10 because it was satisfying to do for me at least. How intuitive would you rate Markov chains? I would say they're pretty intuitive because I mean they make sense, right? Okay. Like should we do this problem? Do you want to do this problem? We could also do this other problem about the frogs. This one I like better because it's a twist on Markov chains. Usually when you're doing Markov chains, you're working with expected value. No, this one gets rid of that and you're dealing with probability instead. But you still use Markov chains, or at least the idea behind Markov chains, which is really cool because you don't see that very often. I'll give this one a 9 out of 10, and I'll give this one an 8 out of 10. Yeah, I already gave it a rating. This one's all right, I guess. Not the most creative problem. I'm pretty sure I've seen this before, and also I don't think it deserves to go in 19. I think it should probably go, yeah, it should probably go earlier. So I'll give this a 7 out of 10 because it's not really creative, it's not very satisfying to solve, and if you were halfway through this problem when the time ended, you wouldn't want to finish it. Or at least I wouldn't. And guess what? I'm the one rating. Aha. This channel is a dictatorship. What are we gonna do about it? Oh, this one is quite nice. This one is quite nice. It uses law of cosines, but it's actually, oh well, maybe for me, it was quite hard for me to notice that you would have to use law of cosines. But okay, here's how it goes. You have 8 and 9, right? You also have another 9 over here. And this length, the one I just drew, was an integer length. This is also an integer length. And what you do is you set this angle to theta, and this is theta right here. So therefore, this right here is 180 minus theta, and you just do law of cosines. Uh, and the calculation is really not that much considering you use law of cosines. Usually when you use that, the expressions balloon into something ridiculously big, but this one doesn't. It's quite nice and simple and things cancel out and it's hard to guess and everything is just nice about this problem. 9 out of 10 again. What the hell? Why is this at 22? Yeah, this is way too easy for 22. Yeah, this one's pretty creative though. I like it. Complex number, it's an actual good use of complex numbers. Where you notice, oh, if this is z, right, and this is the origin. 2z is just over here, right? That one's simple. But, and you might, 1 plus iz, you need to know, like, this property of complex numbers that when you multiply them, it's essentially like a I don't know how to describe it. Well, it's just kind of creative how you have to deal with this before you deal with this. Or you could like it's kind of two separate parts of the problem. You first find out that this equation, the locus is a circle, or like the solution set is a circle with a center 1/2 and radius 1/4, right? In the complex plane. And then you realize, oh wait, the triangle with these vertices is looks like this. And the larger the magnitude of z, the greater the area of the triangle. Great. We'll just pick 3/4. And this is 3/4. And the area of the triangle, if you work out some math, is 3/4 squared. Bang. 9 out of 10. But misplaced. This should probably be like question 15. This one, it does use modular, but I don't really mind it. It's problem 23. You're gonna know how to use modular arithmetic. Yeah, what this, again, I don't know if it's just me, quite hard for me to understand all this crap. It took me a while to realize that all this just boiled down to, if x is greater than y, then 2025x is greater than 2025y mod z. That's basically what this problem boils down to, and yeah, in simpler terms. And also x and y are both less than z. And then the connection you're supposed to make is that if this is true, the only way this is true is if x is congruent to 2025x and y is congruent to 2025y. Yeah. That's all this is. And then you solve this, subtract x on both sides. X is z is a factor of 2024. You add together all the factors of z. There's a way to do that. And if you don't remember the formula or how to find the sum of the factors of a number, you can derive it, which is what I did. And the way to derive it is quite clever, too. Let's go to this one. Uh, I think MAA has been leaning more into these types of questions recently, where you find the intersection of number of intersections of two graphs. Because I haven't seen that before. I've only seen that I've only seen that recently. So this thing is just a and this thing looks like this. Yeah, and you basically find when this starts. Oh, actually, it starts pretty early. It starts like right there, and you find where this starts. And if this were me, I would I would rename I would get rid of this option, and I would add in 401 instead. Because I have to admit, I kind of I didn't really do the problem the whole way. Okay, all I did was that I said, this graph, this logarithm graph, it starts below the sine graph, right? And it ends up above the sine graph. So, what that means is that there are an odd number of intersection points. Oh, well, you can't really know that for sure because you have to check for something like this. If this is the sine graph and the logarithm graph like skims it, then that would be one solution. But then you would have ended up for an even amount of solutions. But it wasn't that hard to check for that. You just have to plug in some numbers. So yeah, after I checked for that, I just realized, okay, wait, this said C398. Oh, it's not these two. It's not these two. And because the sine graph goes like this, not like that. And it can't be these two because they're even, so it's just D. Yeah. And I don't know how to do problem 20. Okay, wait. I forgot to give these ratings. 8 out of 10 and 8 out of 10. Would be 9 out of 10 if they had done this thing right. Or maybe there's another way to easily get the answer. In which case, I would get rid of answers A and B and replace them with like 401 and 402 or something like that, or like 397. I don't know how to do this. So 401 would have been better. Yeah. You don't like the intersection ones? You can get with herons. How come you did it with herons? Okay. Did you? Yeah, I did. I did give a 10 out of 10. It was on. Let me go back all the way. This question. Problem 23, I gave a 10 out of 10 to. I gave a 10 out of 10 to that. Wait, did I say 10 at the start of the stream? No, wait. Okay, I'm just not gonna read chat. Okay, too much is happening. Too much is happening. I don't know how to do this question. Um, I think I've seen it before, so I just kind of guessed, and I guessed wrong. I guessed this, which is kind of stupid. Now that I think of it, because if the answer was this, S would have been 5/2, and there would have been no reason to add this part of the problem in. Also, is this a 6-7 joke? I don't know. Crap. Okay. Yeah. Uh, so I'm not gonna give it a rating because I don't know how to do it. I tried using complex numbers during the test, but I didn't get very far because I don't think the way you do it is with complex numbers. I saw the circles and I thought, oh yeah, you've got to use complex numbers. I don't think it was, or at least I got I ran out of time in the middle, and I had to go back to a previous problem because yeah, I hadn't done problem one at that point. So yeah, uh, that's all for the AMC. That's all for both AMCs. Yeah. Um, put your cam in right. Bang. There we go. Yeah. Okay. Hopefully it doesn't block anything now. Yeah, that's all. I don't really want to work on this problem because I have seen it before in another competition, I think. I don't really know which one. Okay, it's 7 o'clock. Okay. Yeah. Well, that's all for this stream, and I might make a video later, I might not. Who really knows? Who really knows my upload schedule? But yeah, that's all for today. And I'm wait. One of you wanted me to do a puzzle. I don't know who it was. The puzzle was okay. They requested this puzzle in a video in the Discord. If you have a chessboard, okay, chessboard. I'll just write chessboard. So I guess I'll do this puzzle right now. Well, I don't remember. I don't remember exactly what it was. I think it was if you have three queens on a chessboard. How many ways are there to place the queens so that they all attack each other? Oh, is my face? Is my face came there? Okay, I'll move it over here. All right. Yeah. How many ways? I haven't really thought about this site yet. I haven't really thought about this question yet. I don't think it should be too difficult. I'll draw on the chessboard while you guys think. Yeah, this is no longer the AMC. It is clickbait now. Officially, the title is clickbait. Oh yeah, something really funny about this. They said they got this problem from their professor, right? And you might think, well, why doesn't he have the solution to the puzzle? Apparently it's because the professor, like, something happened to the professor, and they just never got the solution to this problem set, which is really fun. Okay, casework. Um, yeah, I think it is casework. I think there are two cases. Here, I will copy this and put it to the bottom. First case is the queens form this kind of shape. By the way, I don't know if collinear counts. Are these queens attacking each other if you have three queens like this? Because this one is technically not attacking this, but from a mathematical standpoint, it might be attacking. I don't really know. So we're gonna count that out for now because It's not too difficult to find the amount of collinear cases. We're just going to assume it's in chess terms, okay? So if you have three queens like this, they can't attack. They're not all attacking each other, at least. This one is not attacking this one. So you have this as a case, and you have this as a case. Is that right? And this case also includes, like, the vertical version as well. Yeah, another version of this problem is that you have to place 8 queens without them attacking each other. Uh, oh yeah, wait. Oh, I did that in one of my, what do you call it? Oh, community posts. I made an estimation minigame. I remember that one. It was the 8 queens problem. Yeah, I think you just have these two cases. Let's go ahead and solve each of them. Yeah, they all have to be right triangles, I believe. Is there any better way to combine these two cases into one? Let's see. If you have a 3 by 3. If you have okay, here's what I'm thinking. Instead of considering two cases, I feel like that would be kind of boring. I feel like we turn this into a 3 by 3 problem. Because look, oh no, that doesn't really work, does it? Okay, what I was thinking was, you see how, look at this 5 by 5. Look at this 5 by 5 real quick. See how, you have queens in these positions, which would kind of correspond to queens in this position? That's what I was thinking. But unfortunately, yeah. So we can't really combine the cases into one. We might as well solve them separately. Okay, let's go. So for this one, you have a square. Um, the number of squares is 64 plus 49. 64 1 by 1 squares plus 49 2 by 2 squares plus dot 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 all the way to 1, right? And then for each of those, there are 4. So multiply 4 times this. Is that right? Should be right. Did we double count any? I don't think we did. Yeah. Because each of these configurations correspond to a square. You can see this one corresponds to the 4 by 4 square. So it would be counted when we wrote down 25. It would be one of the 25 one of the 100 configurations that was in, like, it looked like this, or a rotation of that. Okay, so that's it for this case. How about this? This one I think is a little bit harder. Actually, no, it's not. Yeah, you do it with dominoes. So you can have a 2 by 3 domino here, here, here. 3 by 5. We just continue this problem. Pattern 4 by 7, and that's all we have, right? And you can see this one is a 3 by 5. We have that rectangle there. 4 by 7, and we can't fit a 5 by 9 in here. So, in the chessboard at least. Okay. So, how many 2 by 3 dominoes, or whatever you want to call them, are there here? Well, there are 6 times 7. Oh, wow. Haha. 6, 7. That's hilarious. Yeah, because there are 6 horizontal positions that you can place them in. 5, 6. And there are 7 vertical positions that you can place them in. 5, 6, 7. There we go. So 42 is the face cam blocking again. It's on the right now, right? Yeah, okay. 2 by 3 is 42 of them, and you also have to multiply by 2 because this might not be the only case, like where you have here, here, here. You might also have here, here, here. That's also a valid solution. So you have to multiply by 2. 3 by 5. Hopefully you can see the pattern now. 3 by 5, you have 1, 2, 3, 4, right? It's basically 9 minus whatever this number is. So 9 minus 3 is 6, times 9 minus 5 is 4. So we have 24. Oh, I forgot. Sorry. We also have to multiply by 2 again. Did anyone point that out in chat? Yeah, rotate the dominoes. Yeah, perfect. Remove 64, too small. Yes, you are right. Get 64 out of here. What just happened? Why? Okay. Okay, oops. 64, yeah, 64 is too small. Thank you. Um, and 4 by 7 would be 9 minus 7, which is 2, times 9 minus 4, which is 5. So 10 of these, yeah. The reason we multiply by 2 again here is because dominoes can also be vertical, right? We didn't have to deal with that up there, because rotating a square turns it into a square. But now rotating a horizontal domino turns it into a vertical domino. So we have to make that distinction. 24 times 2 times 2, 10 times 2 times 2. Add all these up and add it to this, and you should have an answer. Let's go ahead and do that right now. Why not? Okay. 4. I don't know why I did them out of order. Plus 42 times 2 times 2 plus 10 times 2 times 2 plus, what was the other number again? 24 times 2 times 2. They're 864. Anyone? 864. Did we do it? Any mistakes? Why shouldn't 1 by 1 count? Because if you have a 1 by 1 square, like, if you have a 1 by 1 square, you can't really fit 3 queens in there. For a 2 by 2 square, you could fit 3 queens. And you can do them 4 separate ways. Yeah, you can do them 4 separate ways, which I just showed. And that's why we multiply everything by 4. That's why 1 by 1s don't count. Yeah. Is this right? I don't know. I make mistakes a lot. You can see I just made a mistake up there. Forgetting the 64. I think we did everything. I think we did everything right. 864 is suspicious. I mean, it's what we got. 2 to the power of 5 times 3 to the power of 3. Yeah, no, I think that's just... Mm, hmm. I wonder if there's any better solution. Yeah, you're probably right. I don't really think so, though. I can't think of any. The one idea I had was to have, like, the 3 by 3 square, which I explained earlier. But, yeah, that doesn't really work. At least I don't think so. Also, question, how far into the IMO... Uh, I haven't really done them. I mean, I've just done problems like, just random problems. I don't really, like, go through them, the team selection tests. When I do problems, I don't, like, take a year and do all the problems from that year. I just, like, skim through them, look at whatever looks interesting, and I do those problems. We can write code for this to test. Okay. You know what? I will ask ChatGPT. Okay. If... Oh yeah, by the way, this can generalize to a larger keyboard, like a larger chessboard as well. You just use the same solution. I believe there are only these two cases for 3 queens. Yeah, you only have these two cases. The right triangle and also the right triangle. Both of them are isosceles right triangles. Yeah, only isosceles right triangles should work. You have an 8 by 8 chessboard. 3 queens. How many ways? Can I use ChatGPT 5? Okay, I'm not gonna log in. So this isn't the best. Okay. Ways to choose. That's not right. Okay. ChatGPT didn't get it, and the other ChatGPT is on my personal account, and I'm afraid I will leak something if I go on there. So we're gonna stick with 864. Unlike my ChatGPT also got 864. Did it get a better solution though? Is the thing. We're fairly sure that 864 is the correct answer, but what about the solution? Yeah, 864. It coded it. Okay, yeah, of course it coded it. That's all ChatGPT does. Okay, yeah. That's it for this stream. I'll probably see you. Okay. I don't know when I'll make a video, of course, but I'll try to get one out today. And yeah, that's it. Bye bye.